These are solutions to an old exam number 3, and I think it lines up pretty well with where we're going to be on our exam 3. It just would have been a little bit earlier in the term than this term. So let's go through them one at a time. A car with wheels of radius 0.4 meters is initially moving at 45 meters per second when it begins applying the brakes. This causes the car to slow to rest with constant acceleration during the next 11 seconds. Find the angular speed of the wheels around the axle, it should say, at time t equals 0, as seen by a passenger moving along with the axle. So in this case, at time t equals 0, we know the axle is moving relative to the ground at 45 meters per second. And we have our relationship for rolling without slipping that says the speed of the axle is equal to r times omega, where omega represents the rotation rate around the axle. So therefore we can solve for omega by doing v axle divided by the radius of the wheel. And that gives us something close to 113 radians per second. Part B, find the total number of revolutions the wheels undergo during the 11 seconds of slowing to rest. So here it's the car is decelerating with constant acceleration, and that means that the angular velocity is changing with constant angular acceleration, and we can use the kinematics equations to solve for the total number of revolutions, but we first need to figure out what the angular acceleration of the wheels is, that constant value. So we can use one of the kinematics equations to solve for alpha. So we know it went to rest, this was 0. Omega initial we just found out was 112.5, and we knew it took 11 seconds, so we can solve for alpha, and in this case, if you call the direction that the wheels are rotating the positive direction, then alpha is negative because it's slowing down. We get minus 10.23 radians per second squared. Then we can use that in a kinematics equation to figure out what the angular displacement of the wheels are, and one way to do it is with the angular displacements versus time. We could have just as easily done the one that involved omega final squared equals omega initial squared and solve for delta theta there. But here we could say wherever it starts at, we'll call that theta equals 0. Whatever rotational position the wheel is in, we'll call that theta 0 equals 0. That's how I thought about it in this problem. And therefore, theta at time t represents the angle it went through. So if I plug in all the information I know, the initial velocity, that negative angular acceleration, we get a certain number of radians out, and we were asked for the number of revolutions, so what we just need to do is change units from radians to revolutions. 1 revolution is exactly the same thing as 2 pi radians, so that gives 98.5 revolutions. Problem 2. A 3 kilogram ball of red putty is suspended by a light string, so this is, you can't see the colors on here, but here's the red putty just hanging from a light string from the ceiling. A 2 kilogram ball of green putty is thrown directly upward away from Earth's center toward the suspended 3 kilogram ball from below. Just after being released, the 2 kilogram ball has a velocity upward of 10 meters per second at a distance of 2 meters below the suspended ball. The 2 kilogram ball rises, sticks to the 3 kilogram ball, so these are like balls of putty, so they sort of flop together and move as a unit afterwards, and the pair rises together to a maximum height before beginning to fall. What is the speed of the 2 kilogram ball just before it strikes the 3 kilogram ball? Well, that's a kinematics problem, right? This 2 kilogram ball has to rise 2 meters, and we want to know its speed when it's risen those 2 meters. It's accelerating downward at 9.8 meters per second squared because it's in free fall. So we can use our kinematics equations and say here delta y is the distance it moves along the upward direction. We want to find v final, and we know v initial is 10, and we know the acceleration y component if plus y is up is minus 9.8. So that allows us to solve for, it's a little bit going a little bit slower when it hits that ball up there, 7.797 meters per second. What is the speed of the combined stuck together red-green ball just after the collision, before it has had time to rise and slow further? So they stick together really quickly and they're moving with some speed just afterwards. We can use conservation of momentum because the impulse approximation, even though gravity's pulling down on them, it gives a very small impulse to the system from just before until just after the collision. It's a very quick collision. So momentum is conserved during that very short collision. Total initial y momentum, well, only the one ball is moving upward and we just found its speed. And then the combined ball has a mass of 5 kilograms and we want to know its final y velocity component. So we get 3.12 meters per second. What magnitude impulse does the 2 kilogram ball of green putty receive from the 3 kilogram ball of red putty during the collision? So in this case, we're just asked for the magnitude. What we're going to do is calculate the y impulse component. If we take the same convention up here, y was up. The 2 kilogram ball is the one on the bottom and the 3 kilogram ball is the one on the top. So if we want the impulse the 2 kilogram ball of green putty receives from the 3 kilogram ball of red putty, it's getting an impulse in the downward direction. But in any case, we don't have to know that. We would just say, if I want to know the impulse delivered to the green ball of putty, that's equal to the change in momentum of the green ball of putty. And the change in momentum is m times Vy final minus m times Vy initial. And we just found both of those speeds, right? Those are the solutions to the previous two parts. So we plug those in and we get a minus 9.356 Newton-second impulse received by the green ball from the red ball during the collision. The y component is negative. We were asked for the magnitude, so I just threw out the minus sign there. 3. A uniform disk of mass 1 kilogram and diameter 1 meter pivots freely without friction in a vertical plane about an axis that is halfway between the center of the disk and its edge. So we've certainly seen disks pivoting around their center. I think there was a homework problem where it pivoted around its edge. This is a different axis. Someone puts an axis perpendicular to the disk and it's halfway between the center and the edge along that certain direction. Okay? So there's where the axis is and it can move around it. So here it's being shown. Here it's pulled up, it could go to a highest point, it could go down to a lowest point. Here it's pulled halfway up, so the center of mass is parallel on a parallel line to the axis, a horizontal line there. And so there it's horizontal. If we let it go, it's going to rotate past B where it's rotated down by 45 degrees, and when it rotates down by 90 degrees, that's the position shown by C, where the center of mass of that object is as low as it can get as it's rotating around the axis. All right, we're told that the moment of inertia for a uniform disk of mass m and radius r around such an axis is 3/4 mr squared. I guess I should think about that for a second. 1/2, and yeah, I think that's correct. In any case, that's not something you could look up in your table of moments of inertia, but here it's just given to you. The disk is released from rest at position A, in which the line joining the axis and the disk center is horizontal, so it's sort of lifted up halfway from its lowest point. It begins to rotate downward at position B. It's rotated downward by 45 degrees, and at C it's at the lowest position, rotated down from A by 90 degrees. Calculate the magnitude of the angular acceleration of the disk at position B. So in this case, at position B, we're just going to say torque net equals I alpha. And in this case, you might want to draw a separate diagram, which I didn't do here, of, the disk rotated at 45 degrees. its center of mass is 45 degrees below the horizontal position. Now, in position A, notice that if we, use the usual approximation that the full weight force is being applied at the center of mass of the disk, which is at the center of symmetry of the disk, there, to calculate the torque, we're going to use torque net equals I alpha. To calculate the gravitational torque, we pretend that that gravitational force acts at the center of mass, and so the moment arm would be half of r, would be half of the radius, right? So in this case, the radius is half a meter, so that's a quarter of a meter. If we were talking about it at position A. At position B, the center of mass has rotated down by 45 degrees, and that means we get an extra factor of cosine of 45 degrees multiplying the quarter meter when we're calculating the moment arm in that case. So torque net equals I alpha, and the only force contributing a torque in this case is the gravitational torque. It has a mass of 1 kilogram, so there's the weight, and it is the distance from the moment arm, from the line that contains that gravitational force vector to the axis of rotation, is 0.25 meters times the cosine of 45 degrees. So that's torque net. We're given the formula for I, so that's 3/4 times m times r squared, r is half a meter, times alpha. So we just solve for alpha in there. B, calculate the magnitude of the angular velocity of the disk at position C. So we let it go from rest at position A, it swings down and it's zooming by C, on its way to going back up again, right? Calculate the magnitude of the angular velocity at position C. Now we can't use kinematics here because the angular acceleration isn't constant, as we explained in the videos. Angular acceleration is large here, it gets smaller and smaller, and it goes to 0 at C. So we can't use our constant angular acceleration equations. Instead, we have to use energy methods. So I'm going to take my system, as we've done so many times in these problems, to be the object that's rotating plus Earth. Gravity is an internal force. We can take whatever the pin is that forms the axis of rotation, that force on the disk we can take to be external, but it doesn't do any work because the point at which that force is being applied isn't moving. So therefore, the net work done by external forces is 0. That's equal to the change in kinetic energy plus the change in potential energy. The kinetic energy, since we just have a rigid body around a fixed axis, it's just the 1/2 I omega squared formula in that case. So it had 0 kinetic energy to begin with. Here's our omega final we're looking for. And in going from A down to C, notice that the center of mass goes from being parallel with the axis to being a quarter meter below the axis. And that means delta y is minus 0.25 meters. So this is the change in potential energy. Solving for omega final, 5.112 radians per second. Calculate the speed in meters per second of the lowest position on the disk at position C. In other words, this outermost point here, it's going, it's moving at some speed as it passes that line C. What is that speed? Here we can use V equals R omega. I'm not sure why I wrote it as omega R, because I usually don't write it that way, but R omega, R is 0.75 meters. Why that R? It's because that R means how far is the point that you want the speed of away from the axis. That's 3/4 of a meter times the omega we just found corresponding to point C, and that's 3.83 meters per second. Problem 4. A merry-go-round at a playground is a uniform disk of mass 200 kilograms and radius 3 meters that rotates in a horizontal plane about a frictionless axis at the center. With what magnitude force should a child push against the edge in the tangent direction as shown in order to give it an angular acceleration of 0.5 radians per second squared? So if we want to know how hard they should push for a given angular acceleration, we can do torque net equals I alpha. And in this case, if the child is pushing in the direction tangent, Remember, if we draw the line that contains that force, the meaning of the moment arm is that perpendicular distance from that line to the axis of rotation. So that means the moment arm is 3 meters. So the torque is F times 3 meters, and we want that to be equal to I times alpha. And I for a uniform disk, this was on the last page of equations that was given out with this exam, the table of moments of inertia, 1/2 mr squared. So we have 1/2 mr squared times 0.5 radians per second squared. That was our alpha. So we're doing torque net equals I alpha, and it's that F that we want to solve for. F is 150 newtons. 5. Two square shapes are cut from the same sheet of metal of uniform thickness. A square of side length 2 meters and mass 4 kilograms, and a square of side length 1 meter and mass 1 kilogram. So they're attached at an edge as shown in the figure, forming a combined rigid planar object. So it's like they're welded together along this line, and they make this object which has the shape of two squares stuck together. We wish to place a frictionless rotation axis at a horizontal distance x from the left end of the object as shown, so that the object will be able to sit in a vertical plane under the influence of gravity, touching only the axis. So we want to put some frictionless axis coming out of the page so that this thing, when it's sitting in a vertical plane, will just be totally balanced on that axis. And if I put my axis too far to the left, it's going to flop downward on the right side. If I put my axis too far on the right side, it's going to flop downward on the left-hand side. Somewhere, if the axis is in the middle, it should be perfectly balanced. That's the point we want to find. And in particular, we want to find that wherever that axis is, what is the distance to the left end? That's what the statement is saying there. What should x be so that it does not tend to rotate in either direction in the configuration shown? So what we need is that the sum of the torques about the axis should be equal to 0. I can think of this, I could think of this as one object, but it's just as well to say, let's take the torque, the gravitational torque due to just this part of the object, plus the gravitational torque due to just this part of the object, because each of those are nice symmetric objects, and we know the center of mass of the left square is at its center, and we know the center of mass of the right square is at its center. So let's calculate the sum of the torques with respect to the axis of rotation, assuming that this distance here, I know this picture is a little bit, it's a bad scan or whatever, but this is supposed to be x. I'm calling this distance from the left edge to the axis x. X is what we want to solve for. This was kind of the most difficult problem on this exam. It was a little bit trickier than maybe the other ones, which are more straightforward. So let's see. With respect to this axis, we have a gravitational force on this part plus a gravitational force on this part. Let's calculate their torques. I'm going to take counterclockwise to be the positive direction. So the left side is exerting a positive gravitational torque on it, and the right side would be exerting a negative gravitational torque. Let's add those two together. The left-hand side has a 4 kilogram mass, so its weight is 4 times 9.8. And how far is that from the position of the axis? Well, if this full distance is x, and this distance over here is just 1 meter, right? Because the full width of this is 2 meters, so this distance is 1 meter. And this is x from the left edge to the axis. Then this little distance from the center of mass to the axis is x minus 1. So the moment arm is size x minus 1 there. Okay, so that's a positive torque. And then the other one's going to be a negative torque, right? Because it's pulling down over here with respect to the axis. It's trying to rotate it in this direction, and that's a negative torque according to my convention for positive rotation directions. So it has a mass of 1 kilogram. So that full weight we're going to pretend is it's being applied at the center of mass of the right piece, right? So it's got a force going down in this direction. Let's see. This is 2 meters, so this is 2.5 meters from the left edge all the way to the center of mass. What I want to know is the distance from this center of mass to the axis over there. So this distance is x. From the left edge all the way over here is 2.5. So if I do 2.5 minus x, that's this distance. So the moment arm in that case is 2.5 minus x. Sum of those two torques equals 0 if I wanted it in equilibrium. We've got a common factor of 9.8 in both terms, so we can divide both sides of the equation by 9.8. It just disappears. And then putting everything together, we get 5x minus 6.5 equals 0, or x equals 1.3 meters for that object. Here is an equilibrium, static equilibrium kind of problem, more like the ones you've seen in homework, perhaps. A pizza restaurant has a sign in the shape of a pizza, a uniform disc of mass 20 kilograms and radius 0.6 meters. It is attached to the side of the building to sit motionless in a vertical plane. The point on the sign closest to the wall is attached to a triangular brace. That's right here. But it is free to pivot around the point labeled pivot. So here's the pivot. I know it's hard to see in this scan, but this disc can rotate freely about that pivot. In other words, it can rotate around there. No friction in that pivot. To keep it from pivoting, we also attach a light cable, effectively massless, from the very top of the pizza sign horizontally over to the wall. The moment of inertia of a disk around a point on its edge is 3/2 mr squared. We'll see why we need that in a minute. First, part A, well, I guess there is no part B in this one, so we don't really need that in this case, but the question is, find the required tension in the cable. I think I gave this because at some point I had a different part where the cable breaks, but I decided it was too long on this exam, so I removed it. So you don't really need that moment of inertia there. Okay, so about the pivot, if this thing is in static equilibrium, the sum of the torques being applied to the pizza sign about this axis should be 0. So we have two torques being applied to it. First of all, the weight of this, we can pretend that that gravitational weight force, which is really distributed over the whole sign, is concentrated and just being applied at the center of mass of the sign, which is at the center of the disk. So I've got a weight force of 20 times 9.8, which has a moment arm with respect to this axis of the radius of the disk, 0.6 meters. That's this torque right here. And if I call the counterclockwise direction rotations positive, that would be a positive torque. Why isn't it rotating around that axis? Well, there's also a tension force being applied right here directly to the left, and it's that tension we want to find out to make the sum of the torque 0. So that tension force T has a moment arm. Remember, to figure out the moment arm, you draw the line that contains that force vector and find the perpendicular distance from that line to the axis of rotation. So in that case, this force also has a moment arm of 0.6 meters. So we have T times 0.6 meters, and that's a negative torque because it's trying to twist it in the negative direction. Sum of those two is 0. When you solve for T, you get 196 newtons of tension force in the cable. Finally, a person drags a box at constant velocity up an inclined plane using a rope that is parallel to the inclined plane surface. Over a 3-second time interval in the middle of the motion, the rope force gives a non-zero impulse to the box, but the change in momentum of the box is clearly 0 during this time. Why doesn't this example violate the impulse momentum theorem? I'm asking you this question in this exam because sometimes people just have a vague notion of, oh, the impulse momentum theorem says the impulse applied is equal to the change in momentum. That's not what it says. More precisely, it says the net impulse being delivered to the object is equal to the change in momentum of the object. In this case, it is true that the rope force gives a non-zero impulse, right? It's pulling in a certain direction for a non-zero period of time, so it's giving an impulse. But it's not the only force on the box. there's also a gravitational force pulling down and also a friction force pulling back along the direction of the plane. It's true that the net impulse from all forces on the box has to be zero, since the change in the momentum is zero. That's what the impulse momentum theorem says too. But just because the net impulse is zero, it doesn't mean that the impulse delivered by one of the forces is zero. So there's no contradiction with the impulse momentum theorem. All right, that was a sample exam that we took a year ago or so.